Hi, I'm Brian Hennessy with Kvaser, and I'm going to do the first half of this webinar that we're doing here joint between Kvaser and MathWorks. And the title of this is Using J1939 Logged Field Data for Data Analysis and Model-Based Design. Kind of a complicated title. Hopefully the material won't be complicated and everybody will learn a whole bunch. So I'm covering the Kvaser portion, the hardware that gathers the data. So it's CAN data that we capture here and we log here, and specifically J1939 protocol. I'm going to talk about the J1939 protocol stack for what we need to know to really understand the ins and outs of this data, logging the data on the data link layer as opposed to logging and filtering and triggering an applications signals in the applications layer, and creating log files and formatting to an MDF type of format for importing into the second half of this webinar, where MathWorks professionals, experts will show how to manipulate and work with this data on the MathWorks level. So the relationship between MathWorks and Kvaser from a product's point of view is fairly simple. They do some very powerful, very excellent software for analysis and simulation, and we have quality hardware for capturing the data for access to the CAN bus. We make some software. All of our software is free. Kvaser Memorator configuration tools is the main software we'll talk about here. Kvaser interface hooks to the CAN bus and provides data directly into MATLAB, and Simulink it provides data into Kvaser Memorator configuration tools as well, and will store and configure that logged data in the appropriate formats for later analysis by MathWorks products as well. So CAN protocol stack, the physical layer and the data link layer here at the bottom is what Kvaser specializes in, and what we cover with our hardware products, and some J1939 specification examples of the specs that actually cover those portions of the stack. The physical layer responsibility is to get the ones and zeros across between devices across the network. The data link layer defines those ones and zeros, defines that raw data, and puts it into a CAN frame for later work by a transport layer, which blocks the data, gets the data from its raw frame across the network. Larger data packages are broken down into usable sizes, transportable sizes in the transport layer. And there's, again, some J1939 specs that handle that, the -21 for classical CAN, the -22 for CAN FD. We're going to mostly be in the classical CAN world today, but I think a lot of what I say will also apply to CAN FD. And then there's the applications up top here, as I've shown it, -71, -73 different application specifications under J1939 that define signals, that define PGN's parameter group, parameter groups, parameter group numbers, signals, offsets, the actual physical or the actual application layer stuff that you need to know, which is why we're doing all this, is to get the actual data across, such as my oil temperature gauge here would be a signal that would be pulled out of a particular PGN out of a package that's defined by these lower layers. So off we go. I'm going to quickly try to get through pretty quickly a little bit about some specific hardware, and then we'll get into the software end of it. So some specific hardware from Kvaser would include, first of all, the Memorator Lite, which is an easy to use, no configuration necessary, 1 GB logging device that will also log 1,000 frames before and after an error event. There's no configuration, baud rate is detected, and it logs the data. It's that simple. It's that easy to use. We have our two main Memorator Pro products, the 2-channel and the 5-channel devices. These are basically the same except for the number of channels they have. They both have a USB connection for a computer connection for configuration and removing data. And when they're used as an interface, they will work as an interface as well. They have an SD card for configuration and log data control, as well as script loading, log data storage. This particular one has a pigtail for 5 channels. This one has a direct to 2 channels. Again, they both will support the USB. So 2 and 5 channel hardware devices that will act as interfaces, CAN bus interfaces, as well as data loggers from Kvaser. Features of the Memorator Pro, so it does work as a standalone device, without a connection to a computer, so it'll get its power from a CAN channel, and it will execute a configuration or a script that's stored within it and log data to its card while just plugged into those CAN buses. Again, 2 or 5 channels, depending on which device you want to get. Simultaneous logging on all channels. It logs the data to an expandable SD card. We've tested at least up to 512 gigs. It takes its power from the USB port or the CAN connector. It's connected to the USB port. It goes into its interface mode and ready to interface with the computer. When it's powered from a CAN connector only, it looks for either a script or a configuration stored internally to execute. It's got some LEDs on it, show you different things it's doing, all defined patterns in the user's manual. It does have galvanic isolation on the CAN bus connections and automatic time synchronization, and you can also use, it has MagiSync, we call it, which will allow it to synchronize to other Kvaser devices on the same computer, same USB, same computer's USB ports. So you can use 2 of these and make it a 10-channel synchronous logger if you use 2 of the 5-channel devices. So moving on quickly here. So Memorator configuration tools, the main piece of software that I'm going to talk about today. Free downloadable from the Kvaser download site. It does a USB connection to your Memorator device. The software does. It creates the KHC file with the configuration information, and it allows you to create a configuration file that does filters, triggers, all in the Memorator Pro device, and allows multi-expression triggers and complex triggers that I'll talk about a little bit. DBC file support as well. So if you want to load a database file so you can work at the signal level or the applications level, you can do that. And it will extract and convert to 14 different common formats. So moving on here. So getting started with the Memorator Pro. So this is a Memorator Pro 5-channel that's shown here. And this is just kind of a quick slide I put together to outline the procedure you'd go through to get this working as a data logger. So you'd load Kvaser drivers for Windows first, download and install from the Kvaser downloads area. Of course, free software. All software from Kvaser is free. You download and install the Memorator configuration tools. If you have hardware, you can hook it up. If you don't, you can do configurations and play with the software before getting hardware to hook up. You run Memorator configuration tools. You configure your triggers, your filters, your expressions, stuff that we'll cover here in a little bit. And then after you capture the data, you can extract into one of 14 different formats that it supports that we'll touch on a little bit as well later down the line. So after installing software, you will see different options for different interfaces. So this is your Windows Start button. Underneath your Start button, you'll see under Kvaser Memorator configuration tools, all of these devices. I've got an arrow pointing to the Memorator Pro 5XHS, which is the device that I have hooked up right now, and I've taken a lot of these screens from. So connecting to the Memorator Pro, once you hit the connect button, once you're running the software and you hit the connect button, you go through this procedure, which we've already covered. You'll see the Memorator Pro 5X listed here, serial number, what USB connection's on. You just click on it and you hit next, and it connects. If you want to pull your data off of a file or something like that on the computer, you can tell it to connect to something other than a Memorator Pro, and it can take data from a file or an SD card directly that's hooked into the computer. Okay, out here I show some of the stuff. If you click on general information, once you've connected to the device, it'll download all of this good information from the device. Some of the other things that we'll cover here in a bit, we'll go through most of these here today. Provided we have enough time. Connecting to the Memorator Pro continued. Once you're connected to the Memorator Pro, you can choose from the menu. And here's an abbreviated version of the menu. We've seen general information. You can configure your buses. In this case, there's 5 different buses, 5-channel device. You can configure them, configure one, configure them all, however many you're using. You can set up your log configuration, define some messages. I'll show a brief example of that. Databases, filters, triggers, scripts, if you happen to be using a T script, I'll cover that as well briefly. And then you can look at your disk information, the logged files on that disk, and your disk management information down here. And I'll show you how to do that a little bit as well, or at least what it looks like. Okay, so bus configuration, CAN 1 and more. Any particular CAN bus you select, you will get a screen to configure that CAN bus. So you want to set your bit rate, your obvious stuff. The more complicated stuff, I'm not going to have time to cover. The synchronous jump width and your chip parameters, I recommend you leave them on defaults for now. Your current settings will show up. If you're in silent mode, if you're in J1939 mode, I've made those active by checking those boxes down here. If you're using CAN-FD, you'd check this one as well. You could apply all of these settings to all different channels. You could set as defaults and use those defaults on all different channels as well. So bus configuration options. So this is just kind of a little graphic about your bus configuration options. Your silent mode disables any transmission in a case of an error frame or a response to the generation of an error frame. You would disable that ability on the CAN bus with silent mode selected. Your J1939 mode applies J1939 rules to the CAN identifier, so it allows you to trigger on PGNs. You know, a CAN identifier in extended CAN is 29 bits, and J1939 defines those 29 bits as a priority, as a PGN, and as a source address. So the J1939 mode allows you to break up that identifier into the finer resolution defined by J1939 and do things specifically on that definition. Then you got your CAN-FD mode, which just lets you run in CAN-FD and use the powers of CAN-FD if your bus is a CAN-FD bus. So log configuration, you want to really confirm that log everything is not on, not selected. Here, that's by default, I believe it is when you load this software, and it's a major, one of the major questions that comes into our support staff. It logs everything when that's selected, and your triggers are ignored. You just log everything. So please make sure that's not checked if you want to use triggers. You can use FIFO mode to either wrap around or tell you when the device is full. It's only going to make a difference if the SD card fills up. You can determine the size of your SD card, the needs to some extent through that page on our website to do use our memory calculator. Looks at your bus bandwidth, your speed, how much data you got on your bus, things like that, and tells you maybe what kind of card you want, depending on the signals you want to log, how long you want to log, things like that. So you can set the time you want to log after power is lost up to 30 seconds on this screen. So that's your log configuration screen. So you can define messages here later in your log configuration screen. This is similar to a DBC file, but it's more isolated to just this program. So you'd be defining and naming a particular message and then maybe a particular signal. So here you'd set up a message rapid position rapid update would be an example of a message of a that's actually an NMEA 2000 message, which is very similar to J1939, so it uses that structure. And here would be a signal within that message, latitude. So this is a message coming from a GPS, and your latitude would be the first 8 bits starting at 0 with a factor of 1. It's kind of a complicated signal, but I use it as an example here for a signal. So you could add a database for a definition of many more messages via a DBC file. So add one or more databases, assign different databases to work with different channels, or the same database to all channels, very flexible there. And once the database is loaded, you can use the messages and the signal names defined within that database, and you can trigger on raw or defined events based on the scaling and the offset in that data applied in that database. Okay, so we're getting down to filters here, I think next. Yeah, log configuration filters. So define up to 64 filters per channel to be applied to the log data before the triggers. So the saying here is don't filter out your trigger events. Careful of that. Filters include options for J1939 formats, as I talked about a little bit. Messages, signals, error frames, external events, PGNs, source and destination. Depending on what you select out here, you'll get different screens to select different combinations of filters in different ways. Your filters can be pass filters, so you only pass certain data that meet your filter criteria. Counting pass, which means you only pass 1 out of 10, 1 out of 5, if you want to do that. Or stop filters, so you stop on this. You stop this particular signal that meets the criteria of that filter. So and this is what that would look like. So again, you can select each one of these, and you'll get different submenus to set up those filters. Triggers. Triggers are very powerful. Typically, you would set up a trigger for a hard-to-find event. You don't want to just log everything. You just want to catch some event. Okay? Then again, you select one of these, and you set up these types of different triggers on a signal, on a full CAN message. External trigger event. You could have a button on the dash that a driver punches when, presses when an event occurs that they want to make sure got logged right. Special events, timer events. So real configurable there. So you use conditions to fine-tune triggers, and you use expressions to set data ranges. So what that means is you set up a condition here. You define a condition like RPM 1200 or RPM low, and you define a condition greater than or less than or equal to, or a number of different ways of defining that condition, and you define what it is, and some timeout data, things like that on it, and then you can define conditions equal to, not equal to, less than any particular condition. So we build trigger conditions with raw or scaled values. Trigger on signals within a specific range of values. And all this lets you do that, a range here or a signal value here. You can select a physical or a scaled value based on a DBC file or a defined signal. And so then triggers can add 1 or 2 expressions that combine up to 3 conditions to control triggering. So you can start, you can stop, you can pause logging based on each expression, and select a pre-trigger and a post-trigger time in milliseconds. So what all that means is, an example here would be my first expression is RPM low. I'm going to start logging. That's the action I'm going to take on that when that expression happens. My pre-trigger size is 1,000 milliseconds, so I've got 1,000 milliseconds of data before that action. And your post-trigger, here we're going to stop logging, and our post-trigger is going to be 30 seconds. and we're going to stop logging with RPM 1200 and trigger 1, whatever those conditions are that are defined in the previous menu. So, or those expressions that are defined in the previous menu. So you select a combination of expressions and how those expressions control actions, which are things that take place on into the memory, start, stop logging, markers, things like that. So very, very flexible there. If you do go with advanced triggers, and here we show with the DBC file loaded, the J1939 temp DBC file loaded, you have a lot of different DBC file defined expressions here. So these are advanced triggers. You can create transmit lists and set the transmit schedule. I've got another slide that makes this a little more clear next time, the next slide. So you can use transmit lists to induce an event, to coax your engine into a particular state that you might want, maybe a regen for a diesel, something like that. You want to try and get your engine to throw a fault. So you want to trick it. You want to send some messages out there to induce a fault on the engine and catch what it does in those conditions. Your transmit list can do that. Configure triggers to send transmit lists as well as control logging. Okay, so let's see how all that works out. So you define your triggers, you define your expressions, up to 8 triggers each per expression, and then you define the actions that are taken with those expressions, and you define a transmit list of messages, and you specify the signal values in that transmit list, and that feeds into your defined actions there. So I find this very flexible, and when I was working on trucks, I really wish I had this at my fingertips. It would have been a lot easier. So any particular presentation with a pro device, in my eyes, isn't complete without at least a mention of T programming. T programming is our scripting language, and it's a C-like language. It's an event-driven language with no real main routine. It's got what we call hooks: on start, on timer, on key hooks. On can message is a real commonly used hook, and then it executes code on those particular events or hooks. We have a complete integrated development environment, free. It's called TRX, and it is within CanLib SDK, also free. You download from our download section. That's our full software development kit. This includes, T programming does include DBC file support. So device output window is there, a send key event window, so you can interact and control your program with different key events, which I find very, very useful. And there's a build window that says if your program compiled right, any errors, things like that. Your custom program will load onto the SD card and run as a standalone device in a Memorator Pro. You can flash that program into memory, so it'll run when that device is used as a standalone device in a vehicle, sent out to catch a rare, hard-to-find event. Please contact me if you want to use T programming. I love to help people with that. Brian Hennessy, bh@kvaser.com, and I will give you some examples of T programming, and I really enjoy working with that technology. It's very powerful for catching and logging data. So we'll talk about our SD card now, which is in the device, and everything is stored on that SD card. When you hit your little flash disk area down here, you will see how much used space you have on that SD card. You can look at your logged files. I'll show you an example of that. It holds your configuration and your log data, and any T program script would be on here as well. So, and you have a disk management option here as well to do different things to your disk, reformat, blank it out, stuff like that. So, under disk management, you manage the SD card through disk management. You check initialize, clear, and test the SD card from here. Here's the options you have to do that. So an example bit of information given about an SD card that I happen to have had loaded in a machine. So disk info, disk check, initialize, clear, and test disk are all possibilities under disk management. Flash disk extract and convert files. So when you go to extract a file, you get this menu here, and you can select what format you want to extract that file in, depending on where that file is going to be used and how it's going to be used. When you list your files, here's some example files that I've taken over the years, and I've got log files, and I've hit list, and I can select any one of those and extract them to any one of these formats in my computer. So very useful, very powerful once you've logged the file. And then we have the conclusions. Memorator configuration tools performs filtering and logging. Now, logging data from one or more CAN buses up to 5 with one device. And it's all free. All Kvaser software is free. Download from the website. Needed for configuring the Memorator Pro, extracting log files, and for flashing a T program and executing that from an SD card in a standalone basis. Memorator Pro can be configured as a custom standalone diagnostic tool with filters, triggers, and log data extraction options. You give it a wide range of applications and lots of different high-level protocols. J1939 can open. I do most of my work with J1939 and NMEA 2000, but it's very powerful for anything, and protocols we don't even know about that have been defined by customers that run on our hardware. We deliver raw CAN data generally through the USB port in other ways, and so we don't get as much into the high-level protocols, although we understand them. Our partners do that, like MathWorks, do it very well, and that's going to be the next part of the presentation. So we'd love to hear from you. Hope this has been of value, and thank you very much.
Thank you, Brian. In the second part of this webinar, we will show you how to use Vehicle Network Toolbox to access J1939 data logged in MDF files from MATLAB and Simulink. We'll start with a brief introduction to the MDF file format by looking at how the file is structured and how traffic from a CAN bus is stored. Next, we will use an MDF file logged from a J1939 network using Kvaser Memorator to demonstrate step-by-step how to read the CAN frames into MATLAB, decode as J1939 parameter groups and signals, use MATLAB to analyze the signal data, and replay the recorded traffic into Simulink for model-based design workflows. Lastly, we'll point you to some additional Vehicle Network Toolbox functionalities that may be helpful. Let's start by looking at the ASAM MDF file format, where ASAM is the standardization organization, and MDF stands for Measurement Data Format. MDF is a binary file format with a few possible extensions. You're likely seeing MF4 more often now for MDF version 4 files, but DAT and MDF are also possible extensions for legacy standard versions. MDF files can be used to store both recorded and calculated data, and it is considered a de facto standard in the automotive industry as of today. Here is a simplified model that helps visualize its file structure. An MDF file contains a number of channel groups, where each channel group contains a number of channels. In most data logging scenarios, you would have a group of signals logged at a particular raster rate, so oftentimes the channel group would contain the time channel used as the synchronization basis for a group of signals or channels. When looking at an MDF file, there are two key elements of interest. Most obvious is the data stored in each channel, but metadata could also be important as it describes the data and could help a consumer of the file decide which data they should focus on. Metadata are defined at all three levels. For instance, the initial timestamp of a file represents when the measurement started. In many cases, the acquisition name of a group contains crucial information about the data recorded. With MATLAB and Vehicle Network Toolbox, you can navigate the file structure very easily and access both the data and metadata. MDF is typically used for recording signal values sent over the vehicle network. But in some cases, the communication itself could be the subject of interest, which means the bus traffic can be recorded by data loggers for later evaluation. The data loggers should follow the rules defined by the bus logging standard so that logged data can be exchanged among different tools. For a CAN bus, the recommended channel names are CAN_frame type. Because only data frames are used for actual data transmission, we will place a lot of emphasis on these as they are important in data analysis and model-based design workflows. Just like a CAN data frame contains several defined fields, a CAN data frame channel is defined as a structure channel that contains a number of member channels. Some members are mandatory, while others are optional, such as IDE, BRS, and ESI. Metadata is important because it can help identify channels of interest. In acquisition name, you will find the bus system name plus the channel number. The source path describes the event type, so you could look for CAN data frame in this field for actual data. The combination of these two are typically sufficient to inform what you should be looking at, but the following three source information fields could also be relevant. Later during the demo, you will see how Vehicle Network Toolbox could help you get to these metadata quickly so you know what data you should be targeting in your workflow. If you recall the file structure diagram a few slides back, here is a slightly altered version showing when the file contains CAN bus traffic. The difference here is an additional layer because CAN data frame is a structure channel with members. From here on, we'll switch to MATLAB to demonstrate how to use the J1939 data in an MDF file logged by Kvaser Memorator for data analysis and model-based design. Our demo is broken down into 4 steps. We're going to show command line interfaces with the help of live scripts. The demo is based on 2 files, J1939database.dbc, which is a database file describing the J1939 network and has information on decoding raw CAN bus data to physical values, and J1939log.mf4, the MDF4 file logged from a J1939 network using Kvaser Memorator. In the first step, we'll read CAN data frames stored in the J1939 log file into MATLAB. Let's first define the MF4 file name in a variable so that we could use the variable later when we need to refer to the file name. Next, we will examine the file metadata by calling the MDF_info function and providing the file name. This returns an MDF_info object with properties representing file metadata. Under Creator Details, we could see that the Kvaser Memorator config tool is used to create the MDF file. We could also see that there are 4 channel groups in total. In order to see details about the channel groups, let's call the MDF channel group info function. We got a table with 4 rows, where each row represents metadata for a channel group. For the purpose of this demo, we're only interested in CAN data frames logged from CAN bus channel number 1. By looking at the combination of acquisition name and source path, we could conclude that the data we're interested in is in channel group number 4. Now that we know the channel group we should focus on, let's use the MDF channel info function to get some details about the channels in this group. Here, we are providing the file name along with a name-value pair to specify the group number as 4. We know from prior introduction that CAN data frame is a structure channel with members. Therefore, we get a table showing all the 11 member channels of CAN data frame along with the time channel named T. The table represents a filtered down set of channels we would like to read data from. You could easily pass this table into the MDF read function as the value for the channel name value pair. The MDF read function would then look at the name and group number to decide which channels it should read from. Now, to examine the CAN data frames in the timetable, we just need to index into the returned 1x1 cell array. We can see all of the 11 defined fields of each CAN data frame, such as the DLC, the data bytes, the data length, and the ID. In step 2, we're going to decode the CAN data frames as J1939 parameter groups and signals using the definitions in the DBC file. Let's first assign the DBC file name to a variable. Next, we will open the DBC file in MATLAB using the CAN database function. A database object is returned with all the necessary information extracted from the DBC file for decoding. Let's open the database object in the variable editor to take a look at its content. You could click into the message info property where you will find information defined for each message. You could further dig into the signal information by double-clicking the signal info struct for a given message and look at its details. In here, you could find useful information about the signals, such as the class, the factor offset, minimum and maximum values, as well as the physical units. Recall that in the previous step, we obtained a timetable with all the CAN data frames. Using this timetable, along with the database object as input arguments, we could call the J1939 parameter group timetable function, which can smartly reinterpret the CAN data frames as parameter groups. The output is packaged nicely again in a timetable format, where each row represents a J1939 parameter group, and you could find all the necessary information, including the name, the parameter group number, or the PGN, the priority, the type in terms of peer-to-peer or broadcast, source and destination address, and the data bytes. Note that the decoded signal values are also available. You're probably interested in getting the values of a particular signal over a time period. The great news is we provide another function named J1939 signal timetable for this exact use case. You just need to pass the PG timetable we just obtained into this function, and it will repackage the signal data for you. Now, you can call this function with just the parameter group timetable, which will repackage signals from all the PGs. However, for the sake of this demo, let's assume we're only interested in two parameter groups, EEC1 and CCVS. We could specify these PG names as the value of parameter groups, and by doing so, we only get back the signals for these two PGs. In the next step, let's take the signal data obtained from the previous step and perform some simple analysis in MATLAB. To make it easier to work with the data, let's extract the signal timetables and assign them to individual variables named CCVS and EEC1. In each timetable, the columns or variables represent the signals. Our first data analysis task is to visualize the engine speed over time, which means we need to look at the data in variable engine speed from the EEC1 parameter group. Let's first filter down the EEC1 timetable to only keep the one signal we need and get the unnecessary information out of the way. To visualize the engine speed signal on a plot, we will use a helper function called plotVar over time, predefined at the bottom of this script. This helper function just calls the MATLAB plot function under the hood. By providing the timetable, the variable name, and the unit, The helper function could plot the requested signal and set the title and axis labels accordingly. Using this helper function, we can plot the engine speed in RPM over time. Our next data analysis task is to visualize the vehicle speed over time, which means we need to look at the data in a signal called wheel-based vehicle speed from the CCVS parameter group. Again, let's first filter down the CCVS timetable to only focus on this signal. As we scroll through the data values, we see that every other time step, the value seems to be resetting to 255.996. To get a bigger picture, let's visualize the signal on the plot. We're using the same helper function as the previous task. Looking at the plot, it confirmed our observation that the signal seems to be resetting to a maximum value, which might indicate a misconfiguration in the logger or some kind of fault of the sensor. In order to make better sense of the vehicle speed data, we should try to clean up the anomalies. Now, recall from step 2 that signal information such as the maximum value is available in the J1939 database object. So why don't we take a look at that variable to find out such information? Let's open J1939DB variable, click into message info, and in this list, we need to find CCVS. After locating the CCVS message, we can click into the signal info to look at the signals. Here, we can see the wheel-based vehicle speed, and by looking at the maximum value, we see that it's 250.996. With the knowledge that maximum vehicle speed is 250.996 kilometers per hour, it certainly doesn't make sense for us to see 255.996 in the data. You could hard-code the value into this vehicle speed max variable, but here is the command to programmatically get that from the object. To clean up the data, we will simply remove the invalid samples. We will use logical indexing to find all the row indices where the sample value exceeds the defined maximum. And we simply set them to empty, which removes the invalid rows. Let's visualize the cleaned up vehicle speed over time. It looks much better now without noises from the incorrect data samples. Now that we have both the vehicle speed and the engine speed, our final data analysis task is to observe them both over time. Because the CCVS timetable and EEC1 timetable are on two different time vectors, we need to first synchronize them to a common time vector so that the data can be aggregated into one timetable. Now, this can be easily achieved using the synchronize function in MATLAB, where we provide the two timetables and specify the new time bases as union, which means the output would contain the time vectors from both input timetables, and the synchronization method as linear, which means using linear interpolation to resample the data. Now that we have a unified timetable, let's use another helper function to plot the two variables, vehicle speed and engine speed. Plot two vars over time is implemented similar to the previous helper we looked at, just for two variables. So that concludes our step 3, where we explored operations on timetable and plotting capabilities. Suppose you're taking the vehicle out for a test drive and something interesting happens. Maybe the drive cycle fails certain criteria, or you suspect there's a bug in your control algorithm. It would be very useful if you can reproduce that state using the recorded data and exercise the Simulink model in the same state for investigation. In the last step, we'll show you how to replay the CAN frames recorded in an MDF file from MATLAB into a Simulink model for offline analysis. Recall that in step 1, We read the CAN data frames from MDF log file into a timetable. Later, in steps 2 and 3, we converted the CAN frames into J1939 parameter groups to work with the signals. However, because J1939 communication happens on the network in the form of CAN frames, the subject being replayed should also be the CAN frames, not the J1939 PGs. To prepare for replaying, we first need to convert the CAN data frames timetable into a slightly different format using the CAN message timetable function. This conversion is required because there may be certain optional elements missing from the MDF data log, but the replay function expects a more rigorously defined format. To do the replay, we'll be using the MathWorks virtual device, which has two channels working as if connected in a loopback manner and emulates the behavior of a physical CAN device. We are going to replay the CAN traffic onto channel 1 and have the Simulink model receive on channel 2. We create a CAN channel for MathWorks Virtual 1 channel 1. Next, we start the channel to put it online. Before we start replaying the CAN messages, let's first look at the receiving end in Simulink. Here is the model we'll be using to receive the PG named EEC1 as an example. We have a J1939 network config block where you can specify the DBC file in use and give a name to this configuration. We'll call it replay. Next, we have a J1939 node configuration block to define a custom node for receiving the replayed traffic. For the J1939 CAN transport layer, we select MathWorks Virtual 1 Channel 2 to be the device in use. Lastly, the J1939 receive block is configured to receive EEC1 using the custom node defined called Node 1. As we receive the PG, we will visualize the 3 torque signals as well as engine speed on the scope. In an actual application, you can pass these signals into another subsystem that contains your control algorithm. Let's start the receiving end first by running the Simulink model. And then we can return to the MATLAB live script to execute the replay function, which starts the transmitting side. As we return to the receiving side to look at the Simulink scope, we can see that data is flowing into the model over the MathWorks Virtual 1 CAN network. So that's the last step demonstrating how you can easily replay recorded CAN traffic into a Simulink model, which allows you to use the data in downstream subsystems for offline analysis. In this demo, we first read metadata and data from an MDF file into MATLAB. Next, we decoded the CAN frames as J1939 parameter groups and signals using a DBC file. We then performed a few data analysis tasks by operating on the timetables and visualizing data using plots. Last but not least, we replayed the logged CAN traffic from a MATLAB script into Simulink for model-based design. Vehicle Network Toolbox has a lot more MDF functionalities that you can check out. Since MDF files can be used to also store calculated data, you might want to write your data analysis result to an MDF file. Some data loggers may produce unsorted or unfinalized files. In that case, you will certainly benefit from the sort and finalize functions. You can actually associate a DBC file with an MDF file as an attachment, and we support attachment operations too. If you're working with multiple files recorded in series, you might want to explore the MDF data store so that you can easily work with a file collection and leverage powerful features in MATLAB such as tall tables. While you visit the product documentation, definitely check out our shipping examples to help you get started. Thank you.